Hi, welcome to Einsrodinger. In this video we are going to see where the need for a fourth dimension comes from in the description that makes of the universe and the theory of relativity. In order to describe the universe we live in, we have to make use of geometry. Geometry is the part of mathematics that explains all kinds of spaces that can exist and the characteristics of each one of them. So, if we explore and we know how behaves the world we live in, then we can say which kind of a space it is. Let's begin our exploration with the simplest model. Let's imagine that we don't know how our Earth is and we suppose that it's flat. Then the world should follow the flat geometry rules, as for instance that when we add all the angles of a triangle, the result is 180 degrees. If we draw small triangles on a paper, on a whiteboard, or in the square of our town or city, we could see that, of course, after make the addition of all the angles, the result will be 180 degrees. But what if we try to do it in a huge scale, on a global scale? Let's imagine we go from Ecuador to the North Pole, from the North Pole then to Gabon, and from Gabon back to Ecuador. What will be the result? If we make the angles and we add them, the result will be 270 degrees. What's the problem? What's happening? Geometry gives us the answer. If we draw over the Earth the 3 points we mentioned and we draw the triangle, we can see that, of course, it's true that every angle has 19 degrees, and when we add them, the result is 270 degrees. The problem was that we supposed that the Earth had 2 dimensions, it was flat. But in fact, it has at least 3 dimensions, and in 3 dimensions we can see that the triangles can have bigger angles, and the result can be 270. Let's take our exploration to a more modern point in which we know that Earth is a sphere floating in the universe. And then we could wonder if there are only the 3 dimensions that we have seen before. So, in order to get an answer, we have to use a new concept, the concept of distance. In order to calculate the distance between 2 points, we just have to draw the smallest possible segment between them and then make a measurement of its length. Another thing that is really important is that the length have to be the same result for anyone, no matter what their position, what their orientation, or what their state of movement. Otherwise, the result will be just a projection. Let's take this plane as an example. We can have this object, we can make a measurement, 25 centimeters, and we can align the object with this direction. In this case, the measurement is quite easy, and we see 25 centimeters. In case we place the object with a certain inclination, when we try to align the object with the direction, the measurement we get is just 15 centimeters, so it's just a projection. If we turn it around, once more, in order to align the object with the direction of reference, then we make a measurement and we find only 20 centimeters. Then that's just another projection. So what's the relation between the length and the projections? It's the Pythagorean theorem. When we have a triangle with a 90 degrees angle, we call hypotenuse the longer side, and we have 2 shorter ones. The relation is this one. So in case we want to calculate the hypotenuse, we need to make this with the values we have found before. the projections, and we can see that the result is effectively the length of the object. And that's the idea about the dimensions. In a plane like this, we can be sure that no matter how the inclination is, we can always find the length with two projections. That's why a plane has two dimensions. Now we are going to do the same with boats with a certain volume. We have this object, it's around 22 centimeters long, and we are going to place it in this box. So, we have to align the object with three directions of reference. We can find the first direction, we can make this alignment, so we see that it's 13 centimeters long. Now we can go to find this direction, the alignment with this direction, and we can see that it's 10 centimeters long. Finally, we can find the alignment with this direction, so we can see that it's 15 centimeters long. We are trying to obtain the result of the length taking into account the three projections. Just like the same with the two dimensions, we have this relation, but now we have to add the third projection. So, in case we need to calculate the length, we only have to write here the values we have found before. So, final result will be more or less 22.2 centimeters. So, it's not hard to see that no matter how the inclination of the object, if I take these three projections, I will be able always to calculate the length. So, in case we have a volume, we have three dimensions. Taking into account everything that we have explained, scientists for centuries thought that the universe had three dimensions because in their measurements they saw that the universe had the properties that we have explained. So, in the beginning of the 20th century, when the scientists were making experimentations with particles moving closer to the speed of light, they saw that the combination of these three projections was not the same for all the observers. And the more you get close to the speed of light, the farther were the difference. So, what's the problem? Well, the question is that in order to have the real measurements of length, they have to add a fourth projection. And that means that the universe has at least four dimensions. What we have explained, of course, have to be understood little by little. But we don't have to forget that it comes from experimental measurements. So we cannot just throw it away as nonsense. Besides, it's we, the humanity, that have to make an effort to understand the universe. The universe doesn't have to load down the reality in order to adapt to our understanding. And what form has this fourth dimension? That's something that we will try to explain in a future video. But until then, let's keep on thinking.